Hello, I'm Álvaro Calafell, and this video is the second part of a review of electrical concepts when voltages and currents are distorted with harmonics. In the first part, we reviewed the concept of root mean square value and active power. Previously, we have learned the origin of harmonics and the characterization of the harmonic distortion. In the present video, we will complete the electrical concept review with the reactive power, the apparent power, and the power factor, as well as introducing the concept of distortion factor. Let's start with the electrical concepts of reactive and apparent power in harmonic conditions. First, it is important to understand the concept of reactive and apparent power in sinusoidal conditions. We already know the expression of active power when we have sinusoidal voltages and currents. We also know that the definition of this power is important because it represents a physical meaning of the power related with the losses, work, and heat in an electrical circuit. This is the power that is used or consumed in an electrical circuit. So, it's the power to transform energy into physical work. Derived from this definition, the concept and definition of reactive and apparent power are also introduced. Reactive power is not generated or consumed, thus, it is non-related to the physical work in a circuit. It is the power used to produce the magnetic and electric fields in conductors and capacitors. It is a power which flows back and forth but does not perform any useful work. The apparent power does not really characterize a physical phenomenon in an electrical circuit. It only indicates the total power involved in the electrical phenomenon in a circuit. Although the only power related to the useful work in a circuit is the active power, the definitions of the apparent and reactive power are also useful in sinusoidal conditions because they are related with the efficiency of the circuit. The apparent power characterizes the maximum active power which can be generated or transmitted to an electrical device. This is produced when the reactive power is equal to 0. In the example below, the maximum active power which can flow through a transformer from the grid to the load is the nominal apparent power of the transformer, and this will be produced when the reactive power consumed by the load is equal to 0. The reactive power is a measure of the use of the current in a circuit. When the reactive power is equal to 0, we are using all the current flowing in the circuit to produce active power. In other words, to produce work. In this case, the current in the circuit is minimum, because we are not using current for the reactive power. In this case, maximum efficiency is accomplished, because with a minimum current, minimum losses are obtained. The review of the previous electrical concepts in harmonic conditions should try to reproduce the same ideas as in the sinusoidal case. With respect to the active power, we learned from the last video that the review comes from the definition of active power, and this expression maintains the same physical concept as in sinusoidal conditions. However, this isn't true for reactive and apparent power, and this has led to a different definition for both powers, aiming to represent the same ideas as in the sinusoidal case. In this way, the apparent power in harmonic conditions keeps the same definition as in the sinusoidal case, which is the product of the root mean square value of the voltage and current. In harmonic conditions, these root mean square values have these expressions as seen in the last video. On the other hand, there are several definitions for the reactive power, trying to reproduce the idea of fluctuating energy between the electrical elements in a circuit and to be useful to characterize the situation of minimum current and losses. This is not a trivial task, because in addition to fluctuating energy in a circuit, we now have the energy related to the harmonics. One of the most used definitions for reactive power comes from the Boudinot power theory, which proposes an equivalent definition as to the active power in harmonic conditions. This definition is the sum of the reactive power from the fundamental and harmonics. This definition does not verify the relation between the apparent, active, and reactive power in sinusoidal conditions, because we have the power related to the harmonic content, which is characterized by the distortion power. Therefore, the Boudinot power theory has the following drawbacks. First, the reactive and distortion powers are not related to the power phenomena in the system. Also, the reactive power does not represent a measure of energy oscillations. There is no direct relation between reactive power, distortion power, and the current's root mean square value. Apparent power cannot be minimized with the help of Boudinot's power model, so that the power factor cannot be increased. To understand better the concept of distortion power, imagine the following example. We have a sinusoidal voltage and a non-sinusoidal current with a third harmonic. We can determine the active power, the reactive power, and the apparent power from the previous definitions. After that, we can determine the distortion power from the previous apparent, active, and reactive power, and obtain that the distortion power depends on the harmonic content of the current. To finish the study of apparent and reactive power definitions, we have the following example. On the left, a linear load consumes this sinusoidal current, and the supply voltage is also sinusoidal. Applying the definitions of power in sinusoidal conditions, we obtain the following results. On the right, a nonlinear load consumes this distorted current, and the supply voltage is also distorted. Applying the definitions of power in harmonic conditions, the active power is the sum of active powers from the fundamental and harmonics. The same is true for the reactive power. Therefore, the active and reactive power are calculated as the sum of the product of the root mean square value of the voltage by the root mean square value of the current by the sinus or cosinus of the phase angles of the voltage and the currents for the fundamental and harmonics. The apparent power is calculated as a product of the root mean square value of the voltage by the root mean square value of the current. The obtained result doesn't verify the relation between the active power and reactive power in sinusoidal conditions. This is due to the presence of the distortion power, which depends on the harmonic content of the voltages and currents. To calculate the distortion factor, we must apply the following expression, which depends on the active, apparent, and reactive power. Let's continue with the definition of the power factor. This definition is derived from the definition of the power factor in sinusoidal conditions, which is that the power factor in harmonic conditions is equal to the ratio between the active power and the apparent power. Both powers are calculated as shown in the screen. If we remember that the voltage distortion is usually small because it is limited to the 5% by the standards, the power factor expressions can be approximated as follows, which can be rewritten depending on the distortion of the currents and the power factor in sinusoidal conditions. So, the power factor in harmonic conditions depends on the power factor in sinusoidal conditions and the distortion of the current, which is characterized by means of the distortion factor. To finish the study of the power factor, we have the following example. On the left, we have the sinusoidal case and the typical expression to determine the power factor in sinusoidal conditions. On the right, the non-sinusoidal case, where the ratio between the active power and the apparent power characterizes the power factor, which can also be approximately calculated from the distortion factors of the current and the power factor in sinusoidal conditions. To complete this video, I'm going to provide you with a script in MATLAB code to calculate the apparent and reactive powers and the power factor. Considering the definitions of these electrical concepts in harmonic conditions, the program first reads the data of the voltage and the current and places the voltage and current in the corresponding vectors. After that, the program performs the Fourier transform for the voltage and for the current and calculates for the fundamental and each harmonic the root mean square value of the voltage and current with their corresponding phase angles. With this information, the program determines the root mean square value of the voltage, the root mean square value of the current, the active power consumed by the load, the reactive and apparent powers, and finally, the power factor.